Okay, so here we have a periodic table. Um, this is the border between metals and nonmetals. So that like jagged diagonal thing is a border.
Okay.
Um, anything to the right are nonmetals. So for example, oxygen, that would not be a metal, right? That's a gas.
Wait,
Or nitrogen.
what about the ones on the border?
We call them semiconductors or semimetals. They have metallic properties, but they don't um, conduct electricity or heat as efficiently
Okay.
as metals do. But metals do get really hot. For example, silicon's a big one. This area is called Silicon Valley for a reason because they produced a lot of microchips back in the day. And those microchips are used to power computers or cell phones. And why use silicon? Because when you have an electronic device that can get really hot, if you use silicon, at least it won't overheat. It won't melt. But at the same time, it can still conduct some electricity.
Okay.
So it's kind of a nice balance between metal and non-metal. Um, these, of course, are metals like chromium or nickel, copper, like, pipes are made of copper. That's a metal, right? Um, sodium would be more like salt. That's a little different. Well, that's sodium chloride, but yeah. Let's talk about periodic trends. We'll start by talking about electronegativity. So as the name implies, it's something that's very negative or likes electrons. Now, this is why you learn about electron configuration beforehand. Like, let's look at fluorine, right? First of all, you have the 1s filled up. Remember, when we fill them up, we do this. So that's hydrogen and helium.
Yeah.
Then you have the 2s, lithium and beryllium. You fill that up. Then you have the 2p, where you see boron, carbon, nitrogen, oxygen, fluorine. So you have to, before you get the fluorine, you do that, then you do that, then you do that. So fluorine looks like that's an electron configuration for fluorine.
Okay.
So fluorine's thinking to itself, wow, I am so close to being full. It's kind of like, for example, if like my son likes Pokemon cards, like he's got a little binder, he's got these sleeves, and maybe he needs one more card to complete a set, or I don't know how Pokemon cards work. I'm just totally making this up. Or he just needs one more card to make it, the book full. So he really wants that card, right? It's kind of the same thing. It's like this really wants an electron, wants it so badly. Just one more, right? So fluorine has a high electronegativity as a result because it wants it so badly. Now let's look at boron. Boron will look like this electron configuration. It doesn't care if that electron as badly as the fluorine does. It's kind of like, okay, I need five more. It's going to take some work, but it's okay. You know, it doesn't want an electron as badly as the fluorine does. The fluorine wants it so badly because it's so close. Does that make sense?
Yeah.
So think of it like that. So when you go along a row, electronegativity increases as you go more to the right.
Okay. So hydrogen would have low electronegativity.
Hydrogen's kind of an exception because it's a 1s, but lithium would have low for sure, or sodium, or potassium, or rubidium. So rubidium has to go past all that way to get this. See, this is like the ideal state. These are called stable. These are gases like helium, neon, argon, krypton, xenon, radon. They're stable because their energy levels are full. So rubidium doesn't really care for that. Um, so that's the deal with electronegativity. Now, going down a group, this will get a little tricky. So let's draw an atom model. So you have a nucleus, right?
Yeah.
Which contains protons and neutrons. Then you have electric clouds. That first cloud is level one. Then level two. Then level three. Okay. So, and you have these electrons floating. Electron, electron, more electrons, right? And remember, the second level can hold up to 8. We'll draw 6. Now, if you think about it, the electron is attracted to a proton. Why is that?
Mm, I don't know.
Well, think about it. You give it too soon. What charge does a proton have?
Positive,
What charge does an electron have?
negative.
So when you have two charges that are opposite, what does that mean? When we put them together,
I don't know.
opposites attract. Think about a I know it's different. Magnets are not quite the same thing, but think about a magnet. Like if you were to put two magnets together, sometimes they stick, sometimes they repel. Why is that? Because magnets have something called north and south pole. The north pole would be attracted to the south pole, but if you put two north poles, they would repel each other. It's kind of the same thing, like opposites attract. Um, Not to sound um, homophobic or sexist or anything like that, but boys and girls, right? Boys and girls tend to attract each other. I mean, but even in homosexual relations, I don't want to get all, gender stuff, but even then, like from my own observation in my lifetime, like sometimes there's one person who's more masculine, one person who's more feminine. And I've seen it with woman relationships and man relationships. The bottom line is that when there's attraction, usually you're attracted to the opposite kind of energy, and that's kind of the same thing here. Um, so protons and electrons will attract each other. There's a force they experience, an attraction. Now, as you can imagine, if an electron is really close to a proton, that attraction is much stronger than an electron that's further away. So, for example, this electron here that I'm pointing at, right?
Yeah.
And this electron over here, that's in this next level. Which one's gonna have a stronger attraction to the nucleus? The one that's closer away or the one that's further away?
Closer.
Closer, yeah. It's like it's getting more excited. It's like, oh,. I see someone I like. So what happens when you go down a group? Clearly, the atom's getting bigger, right?
Yeah.
Because you're adding more levels. It's getting, the radius, and we'll talk about radius in a moment, is getting bigger. So what happens at the outer electrons, or electrons on the outermost level, is not going to have as strong of an attraction to the nucleus as one that's closer in. So the fluorine is pretty close, right? Because fluorine only has two levels. But look at like iodine. That's one, two, three, four. That's a fifth row. The We call them valence electrons, by the way. Valence electrons are a big deal. Have you heard that term, valence electrons?
Yeah.
Yeah, those are electrons that are up on the outermost level. So, well, yeah, I mean, that's obviously further away if you're in the fifth row. So iodine will have a lower iodine has lower electronegativity. Sorry for my bad handwriting, than fluorine. Because iodine's outermost electrons are further away from the nucleus than the fluorine. Fluorine's a little bit closer in. So as you go down a group, so we call those groups, the columns, as you go down a group, the electronegativity decreases. So as you can imagine, cesium or francium would probably have the lowest electronegativity, and fluorine's definitely be one of the highest. Because as you go along the row, you're getting closer and closer to having that full electron configuration that you have like with helium or neon or argon or krypton and so forth. And what really badly wants that electron as you go further to the right. And if you go down, it doesn't want as badly because the outer electrons are further away from the nucleus. So those are called periodic trends, like what trends we notice in the periodic table that helps explain these chemical properties, electronegativity being a chemical property. So I think there might be a really good reference here. Let's see here. Periodic trend reference sheet, maybe that might be good. Well, that's a good one. Yeah. So when I say electron affinity, it's the same thing as electronegativity. It's the same thing. So see how it says here, electron affinity. Affinity means liking. You like something, you have an affinity for something. Increases as you go to the right and increases as you go up.
Okay.
Okay, so this is a very important. This you need to know really well. Your test is on this stuff. Now let's talk about ionization energy. Sorry, atomic radius. Now, how does that tie close to electronegativity? Well,
Is that the same thing as atomic radii?
yeah, yeah. The radius, exactly. Radii is just plural for radius. So here's the deal. I think it's pretty obvious that the radius will increase as you go down a group. As you go down a group, the radius will increase. Well, duh, because you've added so many levels. Of course, that's going to increase. We know that, right? We're good.
Yeah.
As you go along the row, it's a little confusing. Even though fluorine has more protons or is a higher number, um, when you go along the row to the right, the radius will actually, excuse me, decrease. It'll decrease. Why is that? Because what's happening, if I draw like the second row, so you have your nucleus in the middle, By the way, did your teacher talk about the periodic trends this way?
Yeah,
Okay. So this is kind of like coming back to you a little bit.
yeah,
Okay, cool. So electrons, we'll have two electrons in the first level, and then we'll have like a bunch of electrons here. Now, right now, I have four electrons at outermost level. And these electrons, they see the nucleus, so they want to get closer to it. But there's a barrier because you have the first level in the way, the one that has two electrons. But these four electrons on the second level, the second ring, you know, they're starting to cave in a little bit. Like they want to get closer to that nucleus. As you add more electrons, guess what happens? That second level starts caving in a little more because there's more of an attraction, right? Starts caving in a little more. By the time you get to fluorine, you have seven electrons. Even though it's not much of a difference, fluorine is actually smaller. The radius of fluorine is less than the radius of oxygen because fluorine has an extra electron, causing that second level to cave in a little bit more because now there's more pressure. It's like okay, we're getting even. We really want to attract this nucleus. It's kind of like, for example, with my car that I showed you. I mean, obviously, it's not as complicated as chemistry, but I showed this to you, right?
yeah,
Yeah. 'Cause I think I had to cancel an appointment. That's right.
yeah.
Yeah, it was crazy, a crazy day. Yeah, why did the roof cave in? Because there was force from the tree, right? Look at the roof, it caved in. It has mass, right? And that tree's heavy. Um, so think of it like that. Like, and why did my roof cave in more than the other roofs? Because my car was closer to the tree, right?
Oh,
Um, there you go, because there's more mass, there's more force. So that's one thing, something I think about. Um, so that's how atomic radius works. It works like that. So the radius actually increases as you go to the left. Definitely increases as you go down. We know that for sure. So one of the biggest atoms is actually going to be francium. Francium has the lowest has the lowest electron activity, but it's the biggest atom. Because, well, first of all, you have so many levels now, so you've added so many more layers. It's kind of like a building, right? Like if you have more stories, of course, it's a taller building, right?
yeah,
There's also more to the left because it's not the outer level is not going to be pooled in all that much to the nucleus. So that's how atomic radius works. So it works, basically in tandem with electronegativity, it just does the opposite. Then the last one I care about is ionization energy. And by the way, electron affinity, electronegativity, same thing. Now, non-metallic, metallic, we know that. Like, when you're more to the right, you're non-metallic, more to the left, you're metallic. We talked about that already. They have the boundary of the semiconductors. Now, what is your understanding of ionization energy? Or if I ask you to define it, do you know what ionization energy is defined as?
energy needed to remove an electron from an atom.
Okay. So energy needs to remove an electron from an atom. Okay. Now, do you see why ionization would be really high over here and really low over here?
No,
Okay, so let's have that discussion. Thank you for your honesty. Appreciate it. So if you think about it, the fluorine again was this, 1s, 2s, 2p. Okay. So The fluorine really wants that electron badly, right?
Yeah.
So would it want to give up an electron? No, right? Because ionization energy, as you said, was the energy to move an electron. No, it doesn't want to. And it's called ionization energy because when you move an electron, you turn into an ion. Because as you move an electron, it now becomes a positive ion. Well, no, it doesn't want to. Why would it want to give up? It wants to gain, right? So to remove these electrons would take a lot of energy. It's like, no, leave me alone. Now let's take a look at like lithium, for example. So lithium looks like this. Well, lithium needs a lot of electrons to get from here to here. So if it wants to become one of these noble gases, these stable gases, it would rather give up an electron and go backwards to get to helium. Or sodium would give up an electron to go backwards to get to neon. Potassium would give up an electron to go backwards to get to argon. So they'd rather give up an electron. So like, here, take it. Cool. I'm now stable. Let's look at sodium. Sodium is like this, right? Sodium's like, well, I don't really need that extra electron because if I get rid of it, I'm now a stable gas. So those ionization energies are low on the far left. They're very low because it doesn't require much energy. These are high. So ionization energy will increase as you go to the right. It'll increase as you go to the right. So it works in tandem with electron affinity.
So can you go back to the periodic table?
Sure, of course.
Okay, so why? So fluorine would rather go back to helium than neon.
I'm sorry, repeat that again.
Fluorine would rather go back to helium than neon.
No, no, fluorine doesn't want to do that. It would take too much energy because you have to remove 5 electrons.
So then why does
So
it?
it'd rather gain an electron. So the ionization energy is high because it would take a lot of energy to yank off an electron because it's holding onto those electrons badly. It doesn't want to let go. So to yank it off, you're gonna have to use a lot of energy to yank it off.
Okay,
Whereas lithium's like, yeah, take it, go for it. So it doesn't require much energy to remove it. So that's why we see that as a trend. And also, we know that the atomic radius is small as we go further to the right. So that means that there's a stronger attraction between the outer electron and the nucleus, right? So we talked about with fluorine, like you have your nucleus, you have your first level, you have your second level, you got some electrons floating around. Yeah. And so it definitely does not want to give up those electrons. Um, but as you add more levels, and the outer electrons are further away, then like for example, the ionization energy for like somewhere down here is gonna be lower compared to fluorine. If I go back to the periodic table again, like iodine has a lower ionization energy than fluorine because that outermost electron is further away from the nucleus, so it's not doesn't have a strong of a pull towards the nucleus, so it's easy to yank off. So those are the trends. So now if we look at this little thing here, these notes, um, it explains the radius, it's just like a circle. I'm not too worried about that. But it's determined by how much electrons are attracted to the positive nucleus. We talked about that. The fewer electrons in each period, the lesser the attraction. Um, so in general, as we go across a period, which is the row from left to right, the atomic radius decreases. That's because there's more of an attraction between the outermost electrons in the nucleus. See, the valence electrons are drawn closer to the nucleus, decreasing the size of the atom. Now, if we move down, the atomic radius increases because you're adding more levels, as it says right here. I'll send this to you. This is good. So concept checked, which one is larger? Well, N is more to the left of O. K is left to CA. CL is below F, so CL is bigger. BE and NA. BE is more to the right. Um,
Yeah, so
but that's a little tricky, actually. But no,
the
hold
one
on.
with the smallest radius would be Alganison,
Which one?
OG.
OG. Oh, well, no, no, that would, well, no, because it's, w these are kind of an exception. We don't really consider these the last row
So
because
like
now they're stable already. We tend to look more at, um, these here, but the smallest raise would be fluorine.
also it's higher and more down.
Correct. Right. Well, not more down, but it's 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 first of all, it has fewer levels, so it's going to be smaller for sure because of that, and also because you have so many electrons in that outermost level, it's going to be pulled into the nucleus more. But like beryllium and sodium, sodium is definitely a bigger because sodium's more to the left, and it's also a third level. Lithium and magnesium, magnesium is third level, so that'll be bigger. So now we talk about ionization energy, the energy required to remove one electron from an atom, which would be hard to remove. It's definitely hard to remove for chlorine because chlorine doesn't want to let go. Because an outermost level, see, it has like six electrons. One, two, three, four, five, six, seven. So it only has one. So which one's harder? The Cl is definitely harder. Um, have you guys talked about second or third ionization energy?
I don't think so,
Okay,
no.
it's not, we won't get into that. It's fine. So in general, as we go across the period from left to right, the first ionization energy, because we say first because you're removing one. The second means you're removing two electrons. Second, third, you're removing three electrons. Um, Electrons that have the same principal combo do not complete a shield. Um, yeah, so in the same level, um, yeah, so that's why it becomes harder to remove as you go further along the level. Electrons on the same principal combo are generally more strongly bound, right, from left to right. So we see the trend. The electron activity is tendency to attract electrons. Electron affinity, same thing. Um, there's actually numbers that could be used for that, like it's like a 4-point scale. Fluorine has the highest electron activity. CFC has the lowest one. Um, and when you go down a group, it gets lower because you have more shielding for the extra levels. And that's what visual. And it kind of explains a bit more. Going down a group. There's some numbers you could look at. So I think this will be a very good thing for you to consider. Um, so looking at these notes here, we should be able to kind of answer some of these questions now. Do you have a periodic table in front of you?
Yeah.
Okay, give me 1 second. I just need to grab some water. Be right back. Probably electric. It's probably electric.
You need to charge.
But
All you need to put it
next one has a charging station full time. You charge full time. But it's just because I do a lot of driving, that's why it's quite better for me to do.
What is it?
Because I do a lot of driving,
Uh,
electric. Plus, Gavin Newsom, because they're changing the laws. They're giving more incentive for Tesla. Tesla. Yeah. It's come down now much. It's maybe at 30, 40, but it used to be very expensive before.
it's kind of different style. Different style.
Right.
You need the trunk big because you put a lot. You can
Okay. All right. So now that we've had this discussion, what do you think about the first question?
Uh, nah.
So we talked about it goes
Would it be fluorine?
good. Before I forget, actually, hold on a sec. Let me email you. Give me one sec here. Hold on.